And now I want to talk about the allocation problem with enthusiasts. So the setup is like this. We've got a set A of people, and again a finite set and a finite set B of jobs. And now we're going to be interested in the case where the number of jobs is strictly less than the number of people. Okay, so that means that if we allocate the jobs, then some people are going to be left unemployed. We have a subset E of enthusiastic people. And the problem is allocate the jobs. So every enthusiast is employed. And we can't employ everyone because we've not got enough jobs for that, but we can hopefully arrange that all the enthusiasts at least get jobs. And then the theorem is like this. So that for every subset of jobs, we have two conditions. Firstly, we've got the normal plausibility condition that we've discussed previously. The number of candidates for U is at least as large as the size of the set U. And secondly, if we just look at the enthusiastic candidates, okay, so that's CU intersect E, that's the number of candidates who are also enthusiastic people, and that should be at least as large as size of U minus, let's write it like this, okay, so notice that size of B, as I said, is okay, so you've got B here, and then E is a subset of A, so this one might be positive or negative. Okay, so we've got this condition here. Okay, so then the claim is that there's there exists an allocation in which all the enthusiastic people get jobs. And so that's what we need to prove. Okay, so the basic method of proof here is that we're going to set up another matching problem, a different matching problem from the original one, in which and then we'll check the plausibility condition for this new matching problem, and we'll see it's plausible, and so by the original Hall theorem it can be solved, and then from that we'll go back to the original problem. So the way that we set up this new problem is we invent some fake jobs. Okay, so we make up so we've got these fake jobs, and the number of them is size of A minus size of B. Remember, size of A was bigger than the size of B, so this number here is positive. We've got this number of fake jobs, and so that means the total number of jobs. Yeah, so if we put B upper star is B union B prime, so that's the set of real and fake jobs. Yeah, so that the size of that is going to be the same as the size of the set A, because size of B prime is mod A minus mod B. Okay, so now this is kind of looking more like the standard type of allocation problem in which you've got the same number of people as jobs. So let's just write those assumptions again. We've got got our subset E of enthusiastic people, and we've got a set of jobs B, which is smaller than the set of people, and we had our set B prime of fake jobs, and the number of that was mod A minus mod B, and B star was union of B and B prime. So the size of B star is the same as the size of A. And yeah, so and so B star was a set of fake jobs, and we're going to assume, or define more or less, that all the unenthusiastic people are qualified for all the fake jobs, and no enthusiasts. Okay, so the enthusiasts want to do real work, and so they don't count as being qualified for these jobs in B prime. Okay, so this gives us a new matching problem. And we need to understand the candidate sets for this. So let's consider some set of jobs. Some set of the jobs for this new matching problem. So this might contain some real jobs or fake jobs. So here we can write U is V union V prime, where V is U intersect B, which is the real jobs in U, and V prime is U intersect B prime. So those are the fake jobs here. Okay. So we look at the candidate set, and who are the candidates here? So one possibility is that V prime is empty. Okay, so if V prime is empty, so we're just looking at U is just equal to V, and so U is just a set of real jobs, then the candidate set is just the same as we had anyway. It's just the candidate set for V. But what about in the case where V prime is not empty? Okay, so then here you get, well, the candidates for the real jobs, but then also you've got at least one fake job, and you know all the unenthusiastic people are qualified for all the fake jobs. So A less E, that's the set of unenthusiastic people. So that's our candidate set now. We've got the CV. These are the people who qualified for genuinely qualified for the real jobs, and then there's the unenthusiastic people who are qualified for the fake jobs, because we've got at least one fake job in our set U. Okay. And but then there's we can write this in a slightly different way. Let's just rewrite this just a tiny different way. This is CV intersect E union A less E. Okay. So why is this? I mean, here, you know, so here we take all possible candidates for V together with the unenthusiastic people. But we can just sort of restrict attention to the enthusiastic candidates, because, you know, the unenthusiastic candidates, they already appear in A less E, so we don't need to sort of mention them separately. And the point is that this allows us to sort of talk about the size of this set, because this disjoint, these two sets here, these are disjoint. Okay, so in this case, so let's maybe write this separately over here. So we can say that in this case, the size of C star U is equal to the size of CV intersect E plus the size of A less E. That's how the numbers work out in this case, and this is going to be useful because if you remember, one of our basic assumptions was about the size of the set of enthusiastic candidates. Okay, so again, the basic assumptions that we made in setting up this theorem was like this. For any set U of real jobs, we had condition 1 was that the size of CU is at least as large as the size of U, and condition 2, the size of CU intersect E, the number of enthusiastic candidates, is at least the size of U minus the size of B plus the size of E. And and then, as we just said a minute ago, if we've got some set U of real and fake jobs like this, then the number of candidates with respect to the new new matching problem, the size of number of candidates for U is so on the one hand, this is just sorry, let's not talk about the number. Let's just talk about the set for the moment. So this is the set of candidates here. So this is just equal to CV if V prime is empty. And we said it's CV intersect E union A less E. And this was a disjoint union if V prime is not empty. So let's call this case alpha, this case beta. So we want to claim that the size of C star U is always at least as large as the size of U. Okay, in other words, that this extended matching problem, which includes the fake jobs, it still has this plausibility condition. So in case alpha, you've got here size of C star U, well, that's equal to the size of CV, because C star U is just equal to CV here, and that's at least as large as the size of V by this condition that we call 1. But in this case, V prime is empty, so U and V are the same. So we've got that the size of C star U is at least as large as the size of U, which is what we needed. So in case beta, we've got that size of C star U. Okay, so as I said, this union is disjoint, so we've got the size of CV intersect E plus the size of A minus E, which is just the size of A minus the size of E. And then we can use this condition 2 that we had here. So that says that what we've got, the size of CV intersect E is, well, like, okay, we've got this used to be called U, now it's called V. So we've got here, according to this condition 2, we've got size of V minus the size of B plus the size of E plus the size of A minus the size of E. And those guys cancel out. Okay. Okay, but now remember that the size of B prime, the number of fake jobs, was equal to mod A minus mod B. Let's maybe put that little reminder in a box somewhere. We introduced a set of fake jobs, and the number of fake jobs that we chose to put in was equal to mod A minus mod B, to ensure that when we have the real and fake jobs together, that's the same as the number of people. So over here we've got plus mod A minus mod B, so that's the same as adding the size of B prime. Okay. But remember, yeah, we had V was our U was V union V prime, where V was the real jobs in U and V prime was the fake jobs in U. So V prime is a subset of B prime. So the size of V prime is less than or equal to the size of B prime. So we've got this inequality here. Right, and now, so here we've got the size of V plus the size of V prime, but V and V prime, they're just the real and fake parts of U. So this is just equal to the size of U. So putting this together, we've got the size of C star U here. Ends up being greater than or equal to the size of U, as we claimed. So we've shown for all U contained in B star, you've seen that the number of candidates for U is at least as large as the size of U. So this means that this extended allocation problem with real and fake jobs, it satisfies the usual plausibility condition. And so by Hall's theorem, Hall's theorem tells us that this allocation problem can be solved. So we choose a solution. Now remember that we set things up so that size of B star, the number of real and fake jobs, is the same as the number of people. So each person, well, each real or fake job so each person gets a job which is either real or fake. For which they're qualified. Okay. But remember how we set up the qualification rules for the fake jobs. We said that all unenthusiastic people are qualified for all fake jobs, but no enthusiastic people are qualified for any fake jobs. So enthusiasts are not qualified for fake jobs. So they must get real ones. Okay. Okay. So now we just ignore the fake jobs to get an allocation solving the original problem. Okay, so with this, by solving the extended problem, we allocate for each job, each real and fake job, we allocate a different qualified person. Now, if we just ignore the fake jobs, we've still got an allocation of all the real jobs to a qualified person, and and because the enthusiastic people were only qualified for real jobs, and everyone had a job, so that means that every enthusiastic person had a real job. So they still have a real job after we've discarded the fake ones. And that ends the proof of this theorem.